So, essentially we neglect entrance effects, also called edge effects. So, fully developed flow with steady state flow is taken to be incompressible. So, if it is flow between parallel plates driven by a pressure gradient, it is called a Poiseuille flow. And you get a parabolic velocity distribution. This is Poiseuille. Then we have the Kuwait flow problem, where the externally applied pressure gradient is 0. There is no pumping action, and the flow is set into motion by the movement of one surface relative to another. So, here we got a linear velocity distribution. So, if you this is the solution for velocity. The solution for pressure is the x direction, and pressure decreases in the direction of flow for Poiseuille, while for Kuwait pressure is constant. So, these are solutions we obtained, and then there was a problem of flow over an incline. And x and y so here so let us say this is the x direction, and here you have a free surface. And the velocity distribution is again parabolic, like this. And pressure is again constant. Flow is driven by gravity. So, in these problems there is no change in the velocity profile as you go from one x location to another, signifying a fully developed state of flow. If you want to study entrance effects or edge effects or flow development, you have to revert to the full form of Navier-Stokes equations. One extension I wanted to comment on is So, let me exaggerate. So, this is this solid line, this is a linear variation in velocity which is attained under steady conditions. So, think of a problem where the fluid is initially stationary and then suddenly you move the top surface. So, it is going to take some time to attain this distribution. So, initially velocity is 0. So, this is velocity at time t equal to 0 and this is velocity as time t approaches infinity. So, in between there will be a transient phase, so that with increasing velocity with increasing time you go from a stationary fluid medium to a moving fluid medium, the flow being driven by the motion of the top surface. If you want to obtain the complete solution would be not only the steady state, but also intermediate results like this, this curved variation I have shown. So, this is u y t. You want the full solution, then solve the extended form of Navier-Stokes equations. By including this time derivative, which is the temporal acceleration term. So, velocity is now changing with time. So, you have added the temporal acceleration. So, mathematically the initial condition is the fluid is stationary, the boundary conditions are the lower plate is stationary while the top surface is given a velocity capital U for all time t greater than 0. So, somebody mentioned heat equation in this class. So, you have some of you are familiar with equations of this type, and the solution is obtained in books like Kreyszig. The solution is obtained by the method of separation of variables. So, now I remember the solution, so I can write it down, but it may take 1.5 pages of algebra to arrive at the solution. So, this is an infinite series solution where Cn is 0 to h minus So, let me call it a star problem, which means I will not ask you to derive the solution, but if you are interested you can go through it. Now, when you are given a solution, how do you ascertain that it is a solution? First, it should satisfy boundary conditions. If it is an unsteady problem, it has to satisfy the initial condition, and of course, it has to satisfy the governing equations. Okay. So, you can at least check, you can confirm that it will satisfy initial condition, because the Cn is found by imposing initial conditions. It also satisfies boundary conditions, because when y is equal to 0, this entire infinite series is 0 and you get u equal to 0, and when y is equal to h, again sin n pi is 0. So, you have only the leading term, this y over h. So, you get u equal to capital U. So, boundary conditions are satisfied. You also notice that as time t approaches infinity, this t, as it approaches infinity, the infinite series goes to 0 and you get the linear variation. Okay. So, the deviation from steady state is given by the second term, and how rapidly does it diminish? That depends on the exponential term with the smallest value of n. That will tell you how rapidly it diminishes. So, roughly you can check this, some e raised to minus 3 is around 0.01. So, you can define a characteristic time scale equal to 3. Will give you the time constant of the transient process. It roughly, if you ask how long will it take for steady state to be reached, it is given by this expression where nu, what is nu? Nu is mu over rho, and it is called kinematic viscosity. So, you can see that if nu is large, it takes less time to reach steady state. Similarly, if h is small, it takes less time to reach steady state. So, if h is small, plates are very closely spaced, practically immediately you will get steady state, and that steady solution will prevail. If h is large, you have to wait for some time for steady state to be achieved. So, because nu refers to the time it takes for the plate motion to be conveyed to the fluid. So, that is why it is called kinematic. It is a coefficient that determines momentum transfer from the boundary to the interior. So, kinematic viscosity. While mu is dynamic viscosity. Why? Because it gives you the shear stresses acting on the surface. Correct. So, this is under the fully developed approximation. We are writing it. So, when the fully developed approximation is applied, then the spatial acceleration terms are 0. Under that approximation, this is the analysis. Yeah. So, if those are called entrance effects, spatial acceleration effects, edge effects. If those are, if you think they are relevant, they have to be retained. But these are model solutions we have obtained by working with a geometry. These plates are very long. These are two very long plates, and we are looking at the interior. So, expect the edge effects to be small. So, that is often called, that is an engineering approach, that is your real problem is very complicated, but you quickly idealize it. So, this problem is like this, so I work on the simplified model. It is called a modeling step. So, how good is your model? So, you will get some answer and then you have to look at the implications of your solution. If they look reasonable, then your model is correct. So, there is an evaluation of the model that has to be carried out post obtaining the solution. Okay, so just to illustrate these ideas in other coordinate systems, so let us consider flow in a tube. Once again, steady, incompressible, fully developed. So, this is the tube of some radius r. So, when you talk about a tube, you are going to work with RZ coordinate system. And the velocity components are W and let us say u. U and W are the radial and axial components of velocity. Now, the coordinate free form of Navier-Stokes equations will not change, it is the same thing, except that those del operators have to be in RZ coordinate system. So, when you do that, the mass balance equation is written as UR plus U over R plus WZ equal to 0. So, just recall that a term such as WZ is this partial derivative. Similarly, UR is partial derivative of U with R. This is del dot U equal to 0 in RZ coordinate system. So, let us write the R momentum equation, which is rho U R plus W U Z equal to minus pressure gradient plus mu U R R plus 1 over R U R plus U Z. So, this pressure you may write as P or P tilde depending on whether you think gravity is relevant to your problem. And the second term is del square U. Okay, this is the spatial acceleration term, temporal acceleration is 0. And then the Z momentum equation is written in terms of the W component. So, these are the R and Z momentum equations. So, I have already advised you that these equations in Cartesian coordinates you should be able to remember. if you have a problem in rz or r theta, that we will do next, coordinates, then these curvature terms, you can see here there are some extra terms like this, so curvature terms, which go away if there is no curvature. No curvature would be planar. R goes to infinity, the curvature terms go away and you get back your Cartesian coordinates. Okay. So, rz, r theta, mass momentum equations, I will provide you, whether it is a quiz or an exam. You do not have to remember, but it is good to remember. In my value system, memory is a good thing. But do remember Cartesian coordinates. So, now we apply the fully developed flow approximation first to the mass balance equation. What is fully developed flow? Tells you that there are no changes taking place in the velocity components in the z direction. So, you are looking at same velocity, there are no entrance effects to the left. So, there are only no entrance effects to the left, flow is fully developed, you get the same distribution in the axial direction. So, if that is the case, then you get u r plus u over r from the mass balance equation, subject to the boundary condition that the radial velocity on the wall is 0, normal velocity component, there is no flow penetrating or piercing the wall. So, that gives you u equal to 0. So, the transverse velocity, a very important result of all fully developed flow problems would be that transverse velocity is 0. So, there is only one velocity component you have to solve for, and that is the axial velocity. Okay. So, now putting this u equal to 0 in the r momentum equation will give you pressure uniform in the radial direction. Therefore, pressure is only a function of z. Okay. So, this partial derivative of p with z can be written as dp dz. And if you set u equal to 0, this term goes away. You set wz equal to 0, the second term goes away. This wzz is gone because of the fully developed flow approximation. So, you are left only with this part. So, the wz is 0, so w is not a function of z, it is only a function of r. It is not a function of time. Why? Because it is a steady state approximation. So, left hand side is only a function of r, right hand side is only a function of z. It is possible only if each is a constant that we call C1, and subjected to boundary conditions. W at r equal to capital R is 0, and then what are the limits of small r, the radial coordinate? What are the limits of the radial coordinate? R equal to 0, it goes from r equal to 0 to r equal to capital R. What do you know about velocity at r equal to 0? Finite, somebody said finite, somebody said it is a maximum, so the derivative is 0. So, both conditions can be used. So, let us write, this is 1 or this is finite. This finiteness condition helps you eliminate possible singularities at r equal to 0. So, now this is an ordinary differential equation. I am sure you can solve it. You first have to write it as in this form and then subject it to the boundary conditions. So, this will give you, I will write the final answer, I have it. dp dz. So, this is a connection, this is the local distribution of the axial velocity component. Because of this r square term, again it is seen to be parabolic. Now, in most problems, it is not the pressure gradient that is given to you, dp dz is not what is given to you. dp dz is not what is given to you, it is the average velocity, the average flow rate. So, how much is the average velocity? It is 1 over pi r square 0 to capital R 2 pi r w r dr. And if you evaluate, it turns out to be minus r square over 8 mu dp dz. So, you get w, the local velocity divided by w r divided by w bar is 2 times. So, the maximum velocity which is at r equal to 0 is double the average velocity. Okay. So, it is still a parabolic distribution. This dp dz, this is constant C1, therefore, pressure varies linearly. See, W bar is positive, so it is very clear that dp dz has to be negative. So, pressure decreases in the direction of flow. And this you can write as delta P over L. Now, you remember our past discussion related to Moody's diagram, where this flow pressure drop relationship was expressed in terms of friction factor and Reynolds number. So, suppose we recast this analytical result. Let us define friction factor and Reynolds number. See, in those calculations we always worked with diameter. Now, we are working with radius. Why? Because our domain of integration is r equal to 0 to capital R. So, that brought radius into picture. Now, in engineering you never ever use radius. Why? You can't measure radius. I give you a tube, you can measure diameter. Radius comes into picture only in these analytical calculations. Okay. Diameter is what a proud engineer will talk about. So, substituting this delta P over R. So, just if you can construct a relationship between F and RE. And you will get F equal to 64 over RE, okay, for flow through a tube. So, here is an occasion for you to compare with experiments. What experiments? Moody's diagram. Is this result for air? Yes. Is it for water? Yes. Is it for oils? Yes. So, it is for fully developed flow, steady, incompressible Newtonian fluid with a well defined viscosity. It will have this distribution of velocity, and average flow and pressure drop will be related through the dimensionless expression F equal to 64 over RE. And indeed, it matches Moody's diagram. So, this is what we had. This is about RE equal to 2000, and this branch is 64 over RE. So, you can go back to your room or go outside after the class, not now, and confirm that the initial branch is 64 over RE. It is a very powerful validation of the Navier-Stokes formulation. But the next question is, why does it fail for RE greater than 2000? Experiments show that, what experiments? I have shown you the videos, that flow becomes intrinsically unsteady. So, you can no longer drop the time derivative. If you include time derivative, then there is a hope of getting into the second branch. But the first branch holds for steady flow up to RE equal to 2000. Okay. So, there is validation of Navier-Stokes equations for low Reynolds number, that means up to 2000. F and RE get related through 64, this F equal to 64 over RE. So, here you may write steady, here you may write unsteady, and more specifically we had said laminar, and here we had said turbulent. Okay, so our book has many examples in RZ coordinates. I will assign some of them to you. Okay, so it is just that let us say you have an annulus. Can you have, what is this kind, what is this flow? It is Poiseuille flow driven by a pressure gradient. It's some people call it circular Poiseuille flow, flow through a tube. You can also have circular Couette flow, where let us say you have a tube inside which is pulled at some velocity, and you have an outer stationary tube. So, it is an annular configuration. You can also have annular Poiseuille flow, that means it is the annular gap and you have a pressure difference, and there is flow happening in the gap between the two. So, the governing equations, will they change from one geometry to another? No. That is the advantage of this formulation, the same set of equations, but boundary conditions will keep changing as you go from one problem to another. So, geometry comes in through boundary conditions. Usually for unsteady problems, we start from a called quiescent, that means stationary conditions. Fluid is stationary and suddenly you apply a disturbance and the flow starts to evolve and may reach a steady state. Now, we have seen in Moody's diagram, if RE is more than 2000, it will never reach a steady state, it will remain oscillatory. Now, I have not proved it per se, but an interesting observation is, if you work with steady flow, you will always under predict the pressure drop. Okay. Why is pressure drop so important? Because it gives you the pumping power. So, if you did all calculations based on steady flow, then you would get the lower limit of the power requirement. Okay. So it gives you a lower limit, but if you do unsteady, you get a realistic estimate of power to be delivered to the fluid so that you can sustain its motion. Now, let us move on to the r theta coordinate system, also called a polar coordinate system. So, theta is the angle made by this radius vector, you may call it OP, with the positive x axis. So, you could have a physical problem of concentric cylinders. This is an inner cylinder, and this is an outer cylinder, and let us say this outer cylinder is set in motion with some angular velocity omega, and the fluid is in this gap. Of course, the inner cylinder also can move. This is R 1, this is R 2, radii R 1 and R 2. So, the question is, find the velocity distribution in the gap between the two cylinders. So, for that you set up the mass and momentum equations in r theta coordinates, which means you have to express velocities in r and theta. So, let us call this the v component. I think I had used u for radial. So, u is the radial velocity, v is the angular velocity. So, purely in terms of boundary conditions, at r equal to r 1, both velocities will be 0, because stationary cylinder. On the outer wall, the motion is purely in the angular direction. So, v is equal to omega r 2 and u is equal to 0. Okay. Now, if you are going to apply fully developed flow approximation in this geometry, you have to identify a main flow direction, which is the theta direction here. Okay. So, the main flow direction is this is the main flow direction. So, when you go around, you come back to the start. So, that means there are no changes taking place in the flow in the theta direction. That will be the equivalent of a fully developed flow approximation. Okay. As a result, you expect the transverse velocity. What is transverse here? U. This is the transverse velocity. You expect transverse velocity to be 0 and only v to survive. So, under the fully developed flow approximation. So, what about pressure? Now, for flow in a channel or flow in a tube, you could have pressure continuously decreasing, but here it is closing on itself. So, if you say pressure will decrease in the direction of flow, then you come back to the same point. So, you cannot have any reduction in pressure in the theta direction. So, purely by virtue of geometry, the pressure variation in theta direction is also 0, then flow, how is flow sustained? Flow is sustained by the movement of the top surface, outer cylinder, not top, outer cylinder. So, it is like a Couette flow problem in r theta coordinates. So, let us apply these simplifications in r and theta axis. So, let us write mass. So, you have to write u and v. So, I have it here. So, a little more complicated than before. This is the mass balance. This is u into r. I have to, let me put a dot here. So, this is the mass balance equation. Now, v is not a function of theta, that is the fully developed flow approximation. So, that tells you that the first term is 0, and if you apply boundary conditions, what are the boundary conditions? U is 0 on the inner wall, u is 0 on the outer wall. So, you get u. So, you can write since and u r equal to r 1 r 2 equal to 0, u r the transverse velocity is 0. So, just to repeat here, v is this is the direction of v, and this is the direction of u. Okay, this transverse velocity is 0. So, let us write the r momentum equation. See, there is that little calculation of going from the symbol del to the appropriate coordinate system. So, del square in Cartesian coordinates has just the second derivative with x, second derivative with y, but in r theta or r z coordinates there are extra curvature terms. So, I hope you will look into details of vector calculus, convince yourself that those terms will appear. Equal to so, this is like a longish form. So, in coordinate free form, this whole thing in brackets is just del square u. Okay. But when you expand in r theta coordinates, you get all the curvature terms. So, in Cartesian coordinates, this acceleration term was u u x plus v u y, but you have one more curvature term v over r v square over r. So, what is v square over r? What does it remind you of? Centrifugal force, centrifugal acceleration. So, when you do courses on, let us say, rigid body dynamics or particle dynamics, all those acceleration terms are externally added. But when you work in coordinate free form, they appear intrinsically as curvature terms. You do not have to prescribe additional acceleration terms. And you will see that in the theta momentum equation, you will have the Coriolis component. So, these appear automatically, which is the advantage of coordinate free form. Okay. And they are not there in Cartesian coordinates, they appear in cylindrical coordinates, they appear in spherical coordinates. The curvature terms in spherical coordinates are even more involved than Cartesian. But if I give you this equation, you should be able to simplify very quickly. See this u is 0, v theta is 0, fully developed, u theta is 0, okay. But u is 0, so this term is gone, this term gone, u 0, u theta 0, but v is not 0. So, you get a pressure variation So, here you cannot say that the transverse variation of pressure is absent. There is indeed, because of rotation, angular rotation, there is a pressure gradient in the radial direction. Now, in the theta momentum equation, so how do you simplify it? The pressure variation in theta direction is non-existent because of the specific geometry under discussion. So, this is 0, this term is 0, this term is 0, u is 0, v theta is 0, u is 0. So, you have only the viscous terms VRR plus 1 over R VR minus V over R square equal to 0. So, this is a simple ordinary differential equation with two boundary conditions. What are the boundary conditions? Okay. So, this is by solving this equation with those boundary conditions, you will get the distribution of velocity. It is not parabolic, it is, of course, if curvature effects become small, that is the radii become large, this will become a simple Couette flow problem and velocity distribution will approach linearity, otherwise it is not linear. Okay. It is the solution of this equation. So, we will start from this point. On Wednesday, Please come on Wednesday, so there will be some more announcements to help you, not to. There's only one regular quiz pending, one makeup quiz pending.